we can regard every analytic function as a map of the complex plane to the complex plane. You can always regard, if I call W equal to f of z and this is analytic, then what is happening is that every time you give me a value of z in the z plane, you give me a value here, you give me a value in the complex W plane. So this map is f out here. Now the thing about analytic functions is that this map has very specific properties. In particular, just as the lines of constant imaginary z and constant real z are cut each other at right angles, it is the rectangular grid here in the z plane. Similarly, the lines of constant u and constant v, if I call this u equal to u plus iv, recall that because of the Cauchy-Riemann conditions, one of the criteria, one of the consequences of that was that grad u dot grad v was equal to 0. What that meant was that in the W plane, if these are the lines for which the real part is constant, namely u is constant, these are the parts where v is constant on this side, right. Plotted in the z plane, they are going to look like this and something like this, okay. So these curved lines are getting mapped onto this rectangular grid here, okay. Now these two will satisfy the property of conformality, namely that the angle between these is going to be at right angles all the time, and this is a special case of what is called conformal mapping, which says that angles are preserved between curves when you do this mapping. Now you could of course say, alright, is this going to work for the entire plane? Well, is the map invertible is the first question. Suppose I go from z to z squared, for every value of z there is a z squared, but for every value of z squared there is no unique z, because minus z would give you the same point. So the question is, what are the one-to-one maps? What is the most general one-to-one map that you can think of to take you from z to w? It should be invertible and it should be one-to-one. It obviously can't involve anything higher than any higher power of z, it can't involve z squared, z cubed, etc., e to the z, nothing. So the only thing it can do is be a linear map. Okay. So z goes to a z plus b, and that is invertible completely, but it is a sort of trivial map, it does not do anything interesting, it is an extremely trivial map, it means only linear functions, nothing more than that. So this question is a trivial answer. If I say in the z plane, what is the most general one-to-one map? It is a trivial thing. The reason is that the point z equal to infinity is mapped to the point w equal to infinity. If I say w is a z plus b, if z is infinite, w is also infinite. So you have kept that as a fixed point. Now I say no, I do not want to do that. I have the Riemann sphere, the extended complex plane, I have the Riemann sphere, and that is mapped by an analytic function to the Riemann sphere, to another Riemann sphere, and I ask what is the most general one-to-one map from this sphere to that sphere, and I do not say that the point at infinity has to remain the same. This set of points, this sphere on the sphere, should be mapped in a one-to-one fashion, invertible fashion, onto the set of points in the other sphere, and I ask what is the most general map in this case, when the answer becomes very non-trivial, and it turns out that the most general such map, and we will make this very formal, is z goes to w equal to az plus b over cz plus d, where a, b, c, d are arbitrary complex numbers, and in order to make sure that the map does not become degenerate, you require that the determinant not be 0. If the determinant is 0, then this becomes a trivial map, as we will see. So this is the most general map of the Riemann sphere S to the Riemann sphere S, which is analytic and invertible. And this kind of map has a very large number of names. one of which is linear fractional transformations, sometimes they are called fractional linear transformations, but we are going to use for this the term Möbius transformations. So, in the next couple of lectures we will talk about the properties of Möbius transformations. Once we finish that, then we will come back and look at multi-valued functions. So, this means that we are still in the realm of single valued functions, but the fact is that now we have got a very non-trivial situation here because this is not a linear map at all. It should be immediately clear to you that if I multiply A, B, C, D by the same constant number, then in this ratio that cancels out and the point to which Z is mapped does not change at all. Therefore, it is immediately clear that I can take these A, B, C, D and normalize them in some suitable fashion, and I will normalize it in such a way that AD minus BC equal to 1. I can always do this. If AD minus BC is not equal to 1, I will divide each of these coefficients by that number so that the determinant becomes 1 always. Now, this immediately should suggest to you that there is a kind of group property involved here, and we are going to see that in great detail. You see, you can write this ABCD as a matrix, 2 by 2 matrix, and of course when you multiply 2 by 2 matrices you get another 2 by 2 matrix. So, all non-singular matrices will form a group. So, it is clear that these transformations also, provided they also operate in the same way, will also form a group, and we will see that the connection, there is a deep connection between this group of 2 by 2 matrices and the group of Möbius transformations. Let us now take up the study of the set of transformations called Möbius transformations. And these transformations are defined as follows, as I started mentioning the last time. If you ask what is the most general one-to-one map of the complex plane to itself, since it has to be one-to-one, it has to be invertible. There has to be, each Z has to go to a unique W and vice versa. The only thing that you can do is to say Z goes to W equal to some AZ plus B. That is a linear transformation. It's a sort of trivial linear transformation. But you see, this is not very interesting because we know all its properties immediately, and the other point is that it leaves the point at infinity unchanged. So, it is Z equal to infinity maps to W equal to infinity in this case. So, it is as if on the Riemann sphere you have insisted that the point at infinity be unchanged and then asked what is the most general one-to-one transformation between the Riemann sphere of Z and the Riemann sphere of W. But if I relax that condition and simply say that the Riemann sphere has to be mapped to the Riemann sphere in a one-to-one fashion and ask what is the most general possibility, then this is not the most general possibility, but a very interesting thing happens, and one can show that the most general map of the Riemann sphere S to the Riemann sphere S one-to-one, the most general possibility is Z equal to Z goes to W. This is a function of Z which is of the form AZ plus B over CZ plus D, where A, B, C, D are arbitrary complex numbers. That turns out to be the most general map of the Riemann sphere to itself, which is invertible one-to-one, where A, B, C, D are arbitrary complex numbers with just one proviso, and that proviso is that the determinant AD minus BC cannot be equal to 0, because it is easy to see that if indeed AD minus BC should turn out to be 0, then f of Z is a constant for all Z, and that is not a very interesting map. Okay. All the points in the Z plane mapped onto a constant, and that is the end of it. So, we will take AD minus BC to be non-zero in general, and in fact you can go further. You can always divide each of these coefficients by the same number without changing the map. and you can divide by square root of AD minus BC, whatever complex number that is. And once you do that, then the new coefficients will satisfy AD minus BC equal to 1. So we will in general say AD minus BC equal to 1 always. Okay. So now the statement is that this most general map called a Möbius transformation is a map from Z to W, which is defined by this ratio here, such that these coefficients are arbitrary complex numbers satisfying this condition AD minus BC equal to 1, and that is what a Möbius transformation is in the most general case. Now these transformations have a very large number of very interesting properties. They will form a group, a certain group. The group itself will be isomorphic to other groups and so on and so forth, and we will try to classify all possible transformations of this kind. So the task is fairly non-trivial, but the first thing you have to note is what happens to the point at infinity. Well, it is clear that Z equal to minus d over C is mapped to W equal to infinity. So this point Z equal to minus d over C goes to W equal to infinity, that is immediately clear. On the other hand, this also implies, and is implied by the fact that Z equal to d W minus B over minus C W plus A. That is just the inverse transformation. So from Z I go to W, but I invert this and I get dW minus B over minus CW plus A. I could write this down because I am thinking of it always as a matrix A B C D with determinant 1, and the inverse of that 2 by 2 matrix is just D minus B minus C A. Notice that AD minus BC is still equal to 1 in this case. So the transformation has determinant 1, the inverse transformation also is a Möbius transformation, has determinant 1. Now what we need to show in further to show that these form a group is that every transformation has an inverse. We need to show that the product of two transformations is again a Möbius transformation of the same kind, and that is very reasonable to expect that that will indeed be the case, because if I make a further transformation here, it is clear that you are going to get something very similar with just the matrices multiplied, A, B, C, D multiplied, but we will see how this comes about later. Incidentally, that also tells you that the point Z equal to infinity is mapped onto W equal to A over C. So in general, the point at infinity in the original Riemann sphere is mapped to some other point, and vice versa, some other point, the point at infinity there is mapped to something else here. Okay, now how do we go about analyzing all possible such transformations? Well, the first important concept is that of a fixed point. Whenever we look at transformations, one should always ask what points, if any, are left unchanged by this transformation, and then you work around those points. Just as in dynamical systems, and we will see that there is a very close connection between this and what happens in discrete dynamical systems. So let us ask, what are the fixed points of this transformation? These are those points which do not change under the transformation. So they must be solutions of this equation Z equal to AZ plus B over CZ plus D, or CZ squared plus D minus A Z minus B equal to 0. So let us call the roots xi1, 2. These roots are at A minus D plus or minus square root of A minus D whole squared plus 4 BC over twice C. But remember that we have set AD minus BC equal to 1, so I could also write this as A minus D plus or minus square root of, I will make this an A plus D, so you get A plus D whole squared minus 4 AD plus 4 BC So that becomes minus 4 divided by 2c. These are the fixed points of the transformation. So it is clear immediately that at best you can have 2 fixed points for any general transformation, and they are given by xi1 and xi2. Now the reason I wrote it as A plus D is because I am going to use this fact. This A plus D is the trace of a matrix if I write this as A, B, C, D. So there is something invariant going on here, and I would like to write it in that term, in terms of this trace. Okay. So now the following possibilities occur. The first possibility is that xi1, xi2 are finite and distinct. That would mean that C is not 0, there are finite points, and A plus D is not equal to plus or minus 2. That is the most general case that you can have. So C not equal to 0, A plus D not equal to plus or minus 2. Two distinct fixed points somewhere on the Riemann sphere. Now the second case corresponds to xi1 finite, xi2 equal to, well, let us look at the second case would be when they are coincident. So let us say xi1 equal to xi2 equal to xi, which happens C not equal to 0, A plus D equal to plus or minus 2. And this incidentally is equal to A minus D over 2C. So when this thing vanishes, the two roots coincide and they are at the same point, and there is only one fixed point here and it is finite since C is not 0. The third will happen when xi1 is finite. So if C is 0, xi1 finite, xi2 equal to infinity. So this would correspond to C equal to 0, and then you can see immediately that the fixed points, there are two fixed points, and remember that you must have now AD equal to 1 because BC is 0 since C is 0. So this will imply that D equal to 1 over A immediately. And what happens to the transformation? It says Z goes to AZ plus B over D, which is equal to A over D is Z, but AD is equal to 1, so this can be written as A squared Z plus AB. And this has two fixed points, of course. So you have xi equal to, if I bring this A squared here, it is equal to AB over 1 minus A squared, xi1 equal to this, and xi2 by inspection is infinity, because if I set z equal to infinity here, that is infinite here too. So z equal to infinity is a fixed point, but there is another non-trivial fixed point, finite fixed point, which is at AB over 1 minus A squared. So that is the third case, and then the fourth and final case is when it becomes completely trivial. So xi1 equal to xi2 equal to infinity in this case, which will happen when C equal to 0 and A equal to D. So if you set A equal to D and put C equal to 0, then you get just a translation. So this immediately implies Z goes to AZ plus B, A over D, that is Z, plus B over D, that is AB. In this fashion. Okay. And now remember that you must also have AD equal to 1. So it says A squared equal to 1. So this means Z goes to Z plus or minus B. Just a translation, a trivial translation. These are trivial cases, but it is important to have them also in place. So we have four possible kinds of transformations depending on the number of fixed points and where they are. In the case when C is not 0, you have two possibilities. Either you have two finite points which are fixed points which are distinct, or the 2 points are finite but coincide with each other. In both cases the transformation is non-trivial, you still get a linear fractional transformation. But the moment you put C equal to 0, this becomes a linear transformation immediately, and in that linear transformation there are two possibilities. One of them has a finite fixed point and then another one at infinity, and the last one is when the thing is completely degenerate, you just have a shift and nothing more than that. So these are the four, to start with, these are the four kinds of Möbius transformations you could have, but you must remember all the time that the most general case is this, is the most general case, and this is a special case, slightly less trivial. These two are relatively easy, they are just linear cases, they are subsumed in the general transformations. Okay. So far so good, but the next question to ask is, how do we classify these things? I mean, what's the flow, what does it look like, how do these points change, and so on and so forth. For that it turns out to be very useful to introduce a concept called a cross ratio of 4 points. So let us write that down. Cross ratio. So if you give me any four points on the z plane or on the Riemann sphere, z1, z2, z3, z4, I define the cross ratio of these 4 points by this definition, z1 minus z3, z2 minus z4 divided by z1 minus z4, z2 minus z3. So this minus that times this minus this divided by this minus that times this minus this. Okay. That is defined as a cross ratio of these 4 points, and those of you who are familiar with projective geometry will recognize that this cross ratio is the fundamental concept in projective geometry and plays a very important role in that entire subject. Now this cross ratio has some very beautiful points, beautiful features which we are going to analyze and look at. But before that I would like you to verify that the product of two Möbius transformations is yet another Möbius transformation. So they actually form a group. It is a trivial thing to prove, and I am going to assume that you are going to do this and check out that it is so. We have already seen that there is an inverse for each transformation. Okay. So now the important thing about the cross ratio is the following. Under a Möbius transformation this ratio does not change at all. So it remains invariant, and that is not hard to see, because suppose Zi goes to Azi plus B over Czi plus D, and Zj goes to Azj plus B plus C plus D. This will imply that this difference Zi minus Zj goes to, well, let us put the product here, Czi plus D, Cz plus D, and then it is this times that minus this times this, and you can see that the Zi Zj term cancels and you have Ad times Zi minus Zj and B, so let us write this out, ACZi J plus ADZi plus BD plus BC, sorry, BCZJ plus BD minus the same thing, which is ACZJ ZIZJ minus AC minus ADZJ minus BC Zi minus Bd, okay, and this Bd cancels, and what are we left with? This stuff also cancels here, and you have AD minus BC times Zi minus Zj, but AD minus BC is 1. So this immediately tells you the magic trick. This is just Zi minus Zj divided by this denominator out here. And now it is easy to see that if I take IJKL 4 points, then the cross ratio will be unchanged because these denominators will cancel. So this implies that this quantity goes to, is equal to W1, W2, W3, W4 if Zi goes to Wi, where I is 1, 2, 3, 4 under the transformation, then this cross ratio does not change at all, it is invariant. So that is the basic property we are going to exploit in everything, because this is a very crucial thing, this property of Möbius transformations, which will make life very easy now for us. Okay. Now the cross ratio itself of 4 points has a lot of interesting properties, a lot of symmetries. First of all, you choose 4 arbitrary points and you are asking for a cross ratio, but you can define a large number of cross ratios. You can define 24 of them, 4 factorial, because you can write this 1, 2, 3, 4 in any order you like, and therefore from a set of 4 points you can have 24 cross ratios, but all of them are related to each other, and there is only one independent cross ratio, because you can see the following symmetries which are easily established. Let me just for shorthand, let us call, let me write it as IJKL, where this stands for Zi, Zj, Zk, Zl is equal to this. Then the following symmetry properties are immediately obvious, immediately established. IJKL is equal to, if you flip these two, KL Ij, it is equal, does not change at all. It is also equal to Ji Lk. If you flip these two and flip these two, it does not change at all. It is also equal to, if you flip just one part, so this is equal to 1 over JIKL equal to 1 over IJLK in this position. So there are lots of such relations. It is also equal to, this guy is also equal to 1 minus the cross ratio IK JL, and then you can use all these symmetry properties on this and derive all the relations that exist between any 4 points, the cross ratio of any 4 points. So it is a very it's a quantity with a lot of symmetry properties, and the beautiful thing is it is invariant under Möbius transformations. Okay. Now the statement is, I should also mention one more thing. Suppose one of these points is infinity, then what happens to the cross ratio? So let us suppose, for instance, that Z1 is infinite, does not matter, any of these points could be infinity. So infinity Z2, Z3, Z4 is defined as a limit of this as Z1 goes to infinity. So it is just Z2 minus Z4 over Z2 minus Z3. So all you have to do is to take the limit Z1 goes to infinity, and that is it. Okay. So I treat infinity on par with everything else, with every other point, and that is the definition if one of the points is at infinity. Okay. Now with this in place, it is now possible to look at what a Möbius transformation looks like in terms of the fixed points, because there is something very special going on with these fixed points. Under this flow, under this map, the the fixed points alone remain unchanged. So you would like to ask what happens to points in the neighbourhood of these fixed points, what kind of things do they go to. Well, let me point out one thing first, that if you give me any 3 points on the complex plane, say Z1, Z2, Z3 or something like that, and they get mapped to W1, W2, W3, then there is a unique transformation which takes you from the first set of points to the second set of points. Okay. In other words, if on the Riemann sphere you specify for me a Z1, a Z2 and a Z3, and you tell me that these points should be mapped to W1, W2 and some W3, and you specify these, then my assertion is there exists a unique Möbius transformation which will do this mapping one to the other. And the way to prove this is to construct this transformation, just explicitly construct it, and you construct it by considering the following cross ratio: Z, Z1, Z2, Z3, and I know that this is equal to W, W1, W2, W3. I know this has to be true under this transformation, right? And now just write this out, and that is it, and solve for Z, for W in terms of Z, and you know that it is a Möbius transformation and it is unique completely. So there is a unique transformation which takes any 3 prescribed set of points here, any specified set of points, to any other 3 specified set of points there. There is only one and only one Möbius transformation which takes you from one to the other. Now you know that once you specify 3 points on the complex plane, you also specified a circle. So this is a way of showing that a Möbius transformation maps circles onto circles. Okay. So Möbius transformation maps on the Riemann sphere. Now let us go back and look at what our transformation does in terms of the fixed points. So let us consider the following. I will do this for the general case, and then we will look at what happens in the special cases. So we look at Xi1, Xi2 distinct and finite. This case, and remember that Xi1 2 was equal to a minus d plus or minus square root of a plus d whole squared minus 4 divided by twice c, where I have used the fact that AD minus BC is 1. Okay. Now consider this, consider Z infinity Xi1, Xi2. Okay. And I make a Möbius transformation, and what does this go to? Well, Z goes to W. What does infinity go to? A over C. So this goes to A over C. And Xi1 and Xi2 go to themselves, they are fixed points, right. So this and the cross ratio is invariant under this transformation. So this must be equal to that. Okay. Where Z is an arbitrary point and its map is W. So this must be true, which immediately tells me that Z minus Xi1 divided by Z minus Xi2, then infinity minus Xi2, this part cancels out. This is equal to W minus Xi1 times A over C minus Xi2 divided by W minus xi 2 A over C minus xi 1. This must be true. So it says it therefore says that W minus xi 1 over W minus xi 2 is equal to A minus C xi 1 over A minus C xi 2 multiplied by the same ratio. So it is rewritten this projective Möbius transformation in a very suggestive form. It says under this transformation, this ratio, the distance between z and xi 1 and z and xi 2, the ratio of these two numbers is equal to the new ratio, is equal to the old ratio multiplied by a certain quantity, a certain complex number in general, which is a function of the coefficients A, B, C, D of the transformation. So this number, there is a symbol for it, it is equal to k, and it is called the multiplier